Good afternoon and welcome to Gallium Nitride Powering the Future. Today's talk will start with an introduction and basically go over what gallium nitride is. Then I'll delve into the history and development of the material itself. Next I'll talk about how gallium nitride is actually manufactured or made. The next topic would be HEMT devices. That stands for High Electron Mobility Transistor Devices. And that's basically the device that is used with gallium nitride. I'll finish up the talk going over some of the more recent applications of gallium nitride and give you a future outlook. So gallium nitride is rapidly emerging as one of the most important semiconductor materials of the 21st century. With its wide bandgap, high electron mobility, and thermal stability, gallium nitride enables faster, more efficient, and higher power electronic devices than traditional silicon. This presentation explores the original motivation for creating gallium nitride, and I'm calling that the elusive blue LED, as well as a look at more recent applications including power electronics, RF systems, optoelectronics, and aerospace and defense. So let's start by looking at the individual elements that make up gallium nitride. Now you may recall from your high school chemistry class that the structure of an atom is a nucleus made up of protons and neutrons with a cloud of electrons swirling around it. In a neutral atom, the number of negatively charged electrons will equal the number of positively charged protons. Atomic theory and decades of experimentation have shown that the electrons can only occupy certain energy levels or orbital shells. This causes the electrons to segregate into very specific energy bands. So up in the upper right corner is an electron shell diagram for gallium. Now gallium has 31 protons and 31 electrons, and they're organized into 4 energy bands as shown here. Now chemists have a name for all of these bands. However, the outermost band is typically referred to the valence band, and that would be this band on the outside. So the electrons in the valence band are called valence electrons. And notice gallium has 3 valence electrons. Down below here, there's an electron shell diagram for nitrogen. Nitrogen has 7 protons and 7 electrons, and they're organized into 2 energy bands. And notice, nitrogen has 5 valence electrons. So the columns in the periodic table are all organized by the number of valence electrons. And for example, gallium right here sits in column 13 with other elements with 3 valence electrons. So everything in this column has 3 valence electrons. Nitrogen right here sits in column 15, and all the other elements in that column have 5 valence electrons. And notice silicon is right in the middle here, and it's in a column with 4 valence electrons. So you may recall that the optimal number of electrons in the valence band is 8, and elements will try to share electrons by bonding with other elements to accomplish this, to try to get to 8 electrons in the valence band. So silicon starts with 4 valence electrons, therefore it wants 4 more. In a single crystal silicon lattice, each atom forms 4 covalent bonds with adjacent atoms. And I show how this works over here. If we have this blue silicon atom in the middle here, and you can see it's bonding with 4 adjacent silicon atoms and sharing electrons so that its valence band now has 8 electrons in it. And these shared electron bonds are called covalent bonds. Now if we look at the 2-dimensional drawing, so the way silicon gets bonded out is every silicon atom is bonded to 4 of its neighbor atoms in a single crystal silicon lattice. Now this is the 2-dimensional drawing. In reality, it's 3-dimensional as shown here. So single crystal gallium nitride, it wants to do the same thing. So the 3 valence electrons from each gallium atom are shared with the 5 valence electrons of the neighboring nitrogen atoms to come up with 8 valence electrons for each atom. And this creates the regular crystal shown below. And let's take a look at this drawing over here. So every nitrogen atom will share electrons with 4 of its gallium neighbors, and every gallium atom will share electrons with 4 of its nitrogen neighbors. And this gives the valence band for each of these atoms 8 electrons. And again, these are covalent bonds because we're sharing electrons. Here we have a 2D drawing of how this works. Every gallium atom is bonded to its 4 adjacent nitrogen atoms, and every nitrogen atom is bonded to 4 adjacent gallium atoms. Now, in reality, it's not a 2-dimensional lattice, it's a 3-dimensional lattice as depicted in this other drawing. So it turns out that single crystal gallium nitride is very difficult to manufacture compared to single crystal silicon. Single crystal silicon is typically created using the Chowowski technique, where a new crystal is grown by slowly pulling a rotating seed crystal out of a silicon melt. And I kind of show that diagram over here, and we'll talk about that in just a minute. However, this technique doesn't really work for gallium nitride because gallium nitride decomposes before it reaches its melting point under normal pressure conditions. Therefore, more complicated techniques for crystal growth had to be developed for gallium nitride. And I'll talk more about that later. So let's take a look at this drawing off to the right here. The way this works is we have, again, this is for growing single crystal silicon. We have a crucible filled with molten silicon, and we're slowly pulling a seed crystal of single crystal silicon out of this melt, and everything is rotating, and as we pull this crystal out, new crystal forms as this molten silicon solidifies around the seed crystal. This is how it's done for silicon. Again, this technique doesn't work for gallium nitride. So let's review what the term bandgap means by examining another way to draw these energy bands. The bandgap is defined as the energy needed to kick an electron from the valence band up into the conduction band. In a conductor, there's no bandgap because the valence band and the conduction band overlap. This allows electrons in the valence band to easily move because they aren't held tightly by any one atom. Basically, they're free to roam. And let's take a look at this diagram down below here. What we have is our filled shells down on the lower energy levels, and as energy increases, we get into the valence band, and the conduction band and the valence band overlap in a conductor, so there's no band gap here at all. Now in an insulator, the band gap is large. This makes it difficult for electrons in an insulator to jump up into the conduction band. This means the electrons in an insulator are bound tightly to their parent atom, and they're not free to roam at all. And here we have a diagram to show what an insulator would look like. Once again, we have all those filled orbital shells down below here. Then we have the valence band. And then between the valence band and the conduction band is a very large energy gap here. And this, again, is called the band gap. In a semiconductor, the band gap is relatively small. This means it only takes a small amount of energy to kick a valence electron up into the conduction band. This unique property allows us to build electrical devices that can sometimes act as conductors, sometimes act as insulators, and that's what you really need if you want to build something like an on-off switch. And we show a diagram for a semiconductor off to the right here. Once again, we have filled shells and the valence band, but now the difference in energy between the valence band and the conduction band, there's a little gap here, but it's not very much. It's relatively small, and that's why it's called a semiconductor, because sometimes you can jump across this band and move your valence electrons up into the conduction band. So silicon has dominated the industry for many years. However, it's reaching its performance limitations. Both silicon carbide and gallium nitride offer potential advantages in reliability, efficiency, and power density. Silicon carbide and gallium nitride are often referred to as wideband semiconductors. Let's take a look at this diagram below. In silicon, the band gap is about 1.1 electron volts. Silicon carbide has a band gap of 3.2 electron volts, and gallium nitride has a band gap of 3.4 electron volts. So these band gaps are significantly higher than silicon, about 3 times. However, they're not enough to make them an insulator. So these are still semiconductors, they're just wide band gap semiconductors. So here's a table that compares several parameters between silicon, silicon carbide, and gallium nitride. Compared to silicon, gallium nitride and silicon carbide have band gaps that are around 3 times higher, as mentioned before. This means that both can support higher voltages and thinner die. An important difference between silicon and gallium nitride is electron mobility. Gallium nitride has an electron mobility that's over 30% higher than silicon. This makes gallium nitride well suited for many high-frequency applications. And you can see that in the table right here. So both gallium nitride and silicon carbide have breakdown field strengths nearly 10 times higher than silicon. Once again, this means they're able to support higher voltages with significantly smaller and thinner die, and we show that down here. Silicon carbide has a much higher thermal conductivity than silicon or gallium nitride, and this makes it suitable for certain applications where extreme heat dissipation is critical. And for example, the Tesla Model 3 uses silicon carbide FETs in its main inverter that drives the traction motors, and this is for heat dissipation. And we can see that thermal conductivity number down at the bottom of the table here. Now I'd like to go over the history, basically what I call the elusive blue LED. So the red LED, or light emitting diode, was invented by Dr. Nick Holonyak Jr. in 1962 at General Electric using gallium arsenide phosphide. And there's a picture of Dr. Holonyak off to the right here. Now his research in optoelectronics revolutionized the lighting, communication, and entertainment industries and led to the development of the laser diode currently used in CD and DVD players. Now the green LED was demonstrated a few years earlier than that at RCA Labs by Ruben Bronstein and Egon Loebner in 1958. However, it turned out to be too dim to have practical applications. But decades later, in the early 1970s, a team of researchers at Monsanto, led by George Crawford, developed brighter green LEDs using gallium arsenide phosphide, the same stuff that the red LED was made out of. And again, this was made possible by the earlier invention of the red LED. It's just George Crawford's team was able to use nitrogen doping to achieve the green color. So now we had the red and green LEDs. So the next logical step was to create a practical blue LED. You want RGB to get all colors. However, for decades, many researchers tried and failed to develop the blue LED. Now, an LED works by passing electricity through a forward biased PN junction, causing electrons to jump between energy levels and release energy as photons, light. And we show this in this diagram off to the right here. Now, higher energy electrons in the N material, they lose energy as they jump to a lower energy band to recombine with the holes in the P material. Now, in a direct band gap material, this jump produces photons of a certain energy level. Now, silicon's an indirect band gap material, so you don't produce photons with silicon. You just it produces lattice vibration, which is basically heat. However, in direct band gap materials, you produce these photons. Now, the energy of the photon is set by this equation here, and So the energy equals hc divided by lambda, where h is Planck's constant, c is the speed of light, and lambda is the wavelength of light. And if you want light of a certain wavelength, and wavelength in this case means color, you need to produce photons of a very specific energy level. So blue light has a shorter wavelength than red or green. Therefore, you need to produce higher energy photons to create a blue LED. Creating high energy blue photons requires a material with a higher band gap, like gallium nitride or zinc selenide, and all the researchers at the time realized this. However, it turned out that it was much easier said than done. So after 30 plus years of research, some people thought the blue LED might never happen. Enter Tsuji Nakamura, and there's a picture of Tsuji Nakamura off to the right here. In the early 1980s, Tsuji Nakamura was a researcher working at a small Japanese chemical company named Nishia. Nishia had recently expanded into production of semiconductors for manufacturing red and green LEDs. However, by the late 1980s, their semiconductor division was facing stiff competition and mounting losses. Times were pretty tough at Nishia. In 1988, Tsuji Nakamura made a radical proposal to the company's founder and CEO. He wanted to try and build the elusive blue LED that large companies like Sony, Toshiba, and Panasonic had all tried and failed to do. Money was in short supply. However, the CEO took a gamble and diverted $3 million to Nakamura's project. In 1992, after 4 years of constant frustrating work, Nakamura finally created a bright blue gallium nitride LED, relying on earlier work done by Osamu Akazaki and Hiroshi Amano, who were researchers at Nagoya University, which is a very prestigious Japanese university. And I have pictures of Osamu Akazaki and Hiroshi Amano off to the right here. Between 1988 and 1992, Nakamura made several significant breakthroughs. First, he developed a two-flow metal organic chemical vapor deposition reactor and used it to grow near-perfect single crystal gallium nitride by first growing a less perfect gallium nitride buffer layer over a sapphire substrate. Second, he developed an annealing process to produce p-doped gallium nitride. N-doped gallium nitride was already available, but no one could figure out a reliable way to make p-doped in a viable manufacturing process. Number three, he incorporated layers of indium gallium nitride and aluminum gallium nitride into the LED structure itself to increase its brightness. So in 1992, the invention of the blue LED had an immediate effect on Nishia's bottom line. And today, Nishia is a very successful company with over 60% of its revenue related to the blue LED. Off to the right here, we have a diagram showing a stack of what the different layers involved in making a blue LED. And this is brought to you courtesy of this YouTube page here. So in 1996, Nishia added a yellow phosphor over a blue LED to create the white LED that we're all familiar with today. The yellow phosphor absorbs the blue photons and re-radiates them in a broad spectrum across the visible range of light to create white light. And white LEDs are now commonly used for household and industrial lighting. And by the way, I recently replaced the halogen headlights on my truck with much brighter LED lights, and I show those off to the right here. Now notice the high beam, low beam LED placements. There's two different banks of LEDs here. Also notice the yellow color, that's an indication of the yellow phosphor. And also I wanted to point out these LED headlights have cooling fans built into them. Now the LEDs are fairly efficient, but they still generate a reasonable amount of heat. So they have a fan built in to help take some of that heat away. Oh, and by the way, in 2014, Nakamura, Akasaki, and Amano were all awarded the Nobel Prize in Physics for their work developing the blue LED, and maybe more importantly, opening the door to future gallium nitride developments. So let's talk about how gallium nitride is made. If gallium nitride has all these great properties, how come it hasn't replaced silicon yet? And it basically comes down to inertia. After decades of investment, silicon technology is a very mature and capable high volume, high density manufacturing process, and it's great for things like microprocessors, and it can do it at extremely low cost. Gallium nitride, on the other hand, is still an emerging technology that's difficult to manufacture at the same scale as silicon. So let's talk about that manufacturing process. As I mentioned before, we can't grow single crystal gallium nitride boules using the CZ method like we used to, or like we do for silicon. By the way, the term boule, I think, means a round loaf of bread in French. So that's the term used for those columns of silicon that are grown using the Cherhovsky method. So instead, gallium nitride wafers are created by epitaxially depositing a layer of gallium nitride on top of a substrate wafer. So this presents a few challenges. First, we need a near defect-free single crystal gallium nitride to achieve the devices with high electron mobility that we want. However, we're trying to epitaxially grow gallium nitride crystal on a starting crystalline substrate that doesn't match the gallium nitride structure. The lattice mismatch between the starting substrate and the gallium nitride crystal, it just makes things difficult. And one way to think of this is we're trying to make a crystal lattice out of Tinker Toys on top of a Lego substrate. Now I pictorially show this up on the right here. The lattice mismatch doesn't work. So we basically end up with just a bunch of jumbled Tinker Toys on top of our Lego substrate. The answer to this is to add some kind of buffer layer that smooths out the transition between these two layers. And that would look something like this. And sorry, this is not the best picture. It's tough to get AI to draw exactly what you want. But I think everyone gets the idea here. So we're adding all these red Legos as a buffer layer. So what we want to do with this, with atoms, the first step would be to pick a substrate. And the table below shows the main substrate choices and lists some advantages and disadvantages for each. Now at present, the most common substrate used is sapphire because it matches the crystal lattice of gallium nitride fairly closely. However, sapphire is somewhat expensive material. Now silicon is an up-and-coming contender due to its low cost, and there's all this infrastructure out there to build silicon substrates. However, silicon has very poor lattice mismatch and thermal mismatch to gallium nitride. So there's a lot of issues in using silicon, but it's really low cost. So once a substrate is selected, we need to decide on a method for growing the gallium nitride crystal. Several different techniques are available. However, at present, the most common is metal organic chemical vapor deposition due to its excellent thickness control and high throughput rate. This technique heats the substrates to around 1000 degrees C and then introduces gas phase precursors into the reactors. And you can see the substrates on the diagram off to the right here. They're these blue circular discs. So the gallium source is typically trimethyl gallium, and the nitrogen source is typically ammonia, NH3. At the surface of the hot substrates, the precursor gases decompose and the gallium and the nitrogen atoms bond, forming a single crystal gallium nitride layer. As previously mentioned, the lattice mismatch between the substrates and the gallium nitride crystal make it necessary to add a buffer layer or multiple buffer layers between the substrate and the final useful gallium nitride single crystal. Now sometimes gallium nitride is used for that buffer layer, and sometimes other components are used, such as aluminum nitride or aluminum gallium nitride. Now the gallium nitride buffer layer is what Nakamura used in his original experiments. Now there are multiple techniques being used for growing gallium nitride that I didn't mention. I'm just trying to give you the general flavor of how the process works. And let's look at these diagrams down below here. So this diagram on the left, we would start with a sapphire substrate. Then we would epitaxially grow a layer of gallium nitride on here, and this is a buffer layer. And then eventually we would end up growing a higher layer of gallium nitride on here, but this would be single crystal gallium nitride that would give you a high electron mobility. And let's look at this diagram off to the right here, and this is just another way to show it. Here we have our sapphire substrate down below. Next we grow our buffer layer of gallium nitride on top of that, and this buffer layer has defects and dislocations. It's not a perfect crystal, but eventually when you grow another layer on top of it, you end up with single crystal gallium nitride that you can actually use for building high electron mobility devices or useful devices. So now that we have a way to build the crystal structure, let's talk about the devices themselves. And these are called high electron mobility transistors. So the high electron mobility transistor, or HEMT, was invented by Dr. Takashi Momura at Fujitsu in Japan in 1979. A HEMT device is a field effect transistor that employs a junction between two dissimilar materials with different band gaps, aka a heterojunction, meaning a junction formed by more than one material. This is done to create an electron channel instead of using a doped channel like in a normal MOSFET. Now the heterojunction generated channel allows electrons to move with extremely high mobility, giving this type of device excellent frequency performance. Gallium nitride FETs are built using this HEMT concept. Now in the drawing to the right here, the heterojunction is formed between the aluminum gallium nitride layer and the gallium nitride buffer layer. So it's in this region right here shown with this red line. Now the difference in the band gap of these two materials causes significant band bending, and the conduction band dips below the Fermi level near the interface. Now I know these band diagrams can sometimes be a little confusing, but let's just take a look at this diagram off to the right here. This point right here is the interface between the aluminum gallium nitride and the gallium nitride. And when you bring these two materials together, the Fermi levels in both materials have to line up. And the difference in the band gaps between these two materials causes a significant amount of band bending here. And you can see the conduction band actually is bent below the Fermi level in this region right here. Now, anytime the conduction band goes below the Fermi level, you generate a lot of electrons. This creates a plane of free electrons called a two-dimensional electron gas, and that's abbreviated 2DEG. And that forms a conducting channel between the drain and the source. And that conducting channel is shown down below here. Now this conducting channel gives the FET its high performance characteristic, and it can be modulated by a voltage applied to the gate. Now gallium nitride FETs are available in both depletion mode, and that would be DGaN, and in enhancement mode, that would be EGaN. Now notice this device does not have a body diode like most common MOSFETs do. It's just the interface between two dissimilar materials, again a heterojunction, but there's no body diode. So let's take a look at the typical losses in power FETs. So the ideal power FET looks like a perfect lossless switch. So here's our ideal power FET, and here's our lossless switch. However, in reality, there are both resistive and capacitive losses. The resistive loss is due to RDS on, the series resistance, and it's calculated by I squared R. The capacitive loss is due to COSS, which is the parallel capacitance on the transistor, and it's calculated by 1/2 CV squared, and there's going to be a frequency component times F. So the faster you switch this, the higher this capacitive loss is going to be. So for power switching, it's desirable to minimize the total loss being the sum of these two losses. So let's look at each of these losses as a function of transistor size. If we plot the resistive loss of a silicon power FET versus size, we would see something like this red curve shown here. As the transistor gets larger, RDS on decreases, and so does the resistive loss. However, the capacitive loss increases with transistor size. And that's this curve. If we want to minimize the total loss and maximize power efficiency, we would pick a transistor size somewhere around where these two curves cross. Now this is going to depend on the frequency we want to operate, because this capacitive loss changes with frequency. So what would the same curves look like for a gallium nitride FET? So due to its high electron mobility, the RDS on of a gallium nitride FET starts off lower than a similar size silicon FET. And we show that in blue here. In addition, the resistance of the gallium nitride FET drops off steeper as its size increases. The capacitive loss in a gallium nitride FET is also lower than its silicon counterpart. And this is partially due to the absence of that body diode we talked about in the heterojunction transistor. So this leads to a shallower capacitance loss curve for the gallium nitride FET. So this graph illustrates some of the major advantages of gallium nitride power FETs versus standard silicon FETs. The smaller size gallium nitride FET can operate with a lower power loss than its silicon counterpart. Lower losses equate to less heat, which leads to smaller packages with less heat sinking required. With gallium nitride, you can sacrifice some efficiency to push the switching frequency higher, and you could still be more efficient than the silicon counterpart. And this is great for some RF application. So if you wanted to push the frequency, you would actually increase the losses, these capacitive losses, but you could still be lower loss than the silicon counterpart. So let's examine the typical efficiency improvement achieved by using gallium nitride to build a switching power supply. So this graph shows efficiency as a function of load. At light load, a typical silicon-based power supply might start out at about 80%. This increases to maybe 90% at higher loads. Using gallium nitride, the typical efficiency curve starts out higher at lighter loads and tops out at roughly 93% for heavier loads. So at first glance, this 3% increase in efficiency, it may not seem like much. However, let's look at it from a power loss percentage. The typical silicon-based power supply has a 10% loss. Gallium nitride reduces that loss to 7%. This translates to a 30% reduction in loss and a 30% reduction in unwanted heat. This allows you to build a smaller device or system and use less heat sinking. As an example, I pulled this picture from a YouTube video that compares the volume, mass, and construction of two roughly 50-watt switching power supplies. That YouTube video is shown down below here. The first supply is constructed using silicon components, and the second supply using gallium nitride components. The gallium nitride supply is only about 1/3 the mass and 1/3 the volume of the silicon supply, and much of this improvement is due to the need for less heat sinking. And let's take a look at this photograph here. You can see that the silicon supply is about 134 grams, where the gallium nitride supply is roughly 45 grams. And you can see the size difference also. The circuitry, if you watch this video here, is not exactly the same, but it's very, very similar.
So gallium nitride is now worldwide. And to demonstrate that, I recently took a trip to Thailand. And of course we saw some beautiful sights in Thailand. But while we were there, we stopped at a 7-Eleven. While we were standing in line at 7-Eleven, my wife was purchasing a few items and I was trying to stay out of the way with my back against a wall. Well, it turns out that wall was filled with phone chargers. So I started looking at the phone chargers themselves. And sure enough, the phone chargers are advertising internally gallium nitride inside the phone charger. So there you have it. Gallium nitride is now worldwide, as being demonstrated by a nondescript 7-Eleven in Bangkok. And I had to take this picture because I knew I'd be giving this presentation in 2 weeks.
Now I'd like to spend a little time talking about gallium nitride applications. And the first application is one we've already hit upon, is optoelectronics. And it turns out gallium nitride is a crucial element in optoelectronics. And we've hit on this already, basically for LED lighting and backlighting. It's also used in laser diodes and Blu-ray players, and that gives you high density and high data storage. Fiber optic communication, and it's also used in detection and ranging. That's LiDAR and other optical sensors. And LiDAR is extensively used in autonomous electric vehicles now. Another optoelectronics application is in ultraviolet emitters and sensors. Gallium nitride is being used in producing UV light for sterilization of water and air surfaces, and also as a sensor for flame sensing. This gives you early detection of flames in homes, and it can also be used as detection of missile launches. And the last item I wanted to talk about here is displays. It can be used as backlighting and as possibly direct emission micro LED displays in the future here. The next application I wanted to talk about is power electronics, and we've already hit on this a little bit. And gallium nitride is revolutionizing power electronics. USB fast chargers, and we've already mentioned those, and you can see the reduction in size from the previous slide. Servers and data centers, reducing the energy consumption and heat. These data centers use a lot of power. Portable devices, being more efficient, will extend your battery life of portable devices. Automotive onboard chargers. This gives you a higher power density for faster charging of electric vehicles. Motor drives. Motor drives for robotics, drones, and electric vehicles. And the last topic I wanted to mention was solar power, not necessarily for the photocells themselves, but for the inverters, where you're converting the low voltage produced by the solar cells into a higher voltage used for charging a battery. The next application I want to talk about was radio frequency, or RF. And gallium nitride provides the power and speed necessary for many modern RF applications. And I've just listed a few of them here. We have 5G base stations. These are the power amplifiers up on the cell towers. Military radar. Right now, gallium nitride on silicon carbide is being used in the active electronically scanned array, that's AESA radars, for smaller size, lighter weight, and increased range and resolution. By the way, this is the type of radar used with the Patriot missile right now. The last two topics are satellite communication for higher power amplifiers, and we've already mentioned for autonomous vehicles, you have LiDAR systems. Gallium nitride applications in aerospace and defense. GaN enables smaller, lighter, and more efficient systems. We've already mentioned radar systems in the previous slide, and again, this is what the Patriot missile uses at present, electronic warfare, high power amplifiers for jamming and electronic support, communication, secure military radios due to radiation tolerance. Gallium nitride has excellent radiation tolerance, and that's good for military radios, directed energy weapons. And we're talking about microwave weapons for disabling drones. Gallium nitride is very well positioned in this area. Unmanned aerial vehicles, lightweight components extend the flight time and improve your payload capacity. And the last topic is space. The high efficiency, smaller size, radiation tolerance, and ruggedness of gallium nitride is ideal for satellites, CubeSats, and robotics in space. The last application I want to talk about is high radiation environments. And gallium nitride is an excellent material for radiation tolerant circuits, offering superior performance due to its wide band gap, which makes it inherently resistant to heat and radiation. I've heard many gallium nitride circuits have total ionizing dose of 1 megarad silicon, which is excellent. So applications would be in spacecraft for deep space, long duration missions where you're going to get a lot of radiation. Maybe inside a nuclear reactor for safety monitoring and control systems. And in fusion research where gallium nitride could be used in part of the diagnostic systems. The last topic I want to talk about is the future of gallium nitride. And this first slide is just a market summary. So what does the future hold for gallium nitride? And multiple industry forecasts point to strong expansion. The global gallium market could double between 2025 and 2035 with an estimated 7 to 8% compound annual growth rate. Some predict even faster growth driven by telecom, electric vehicles, and defense demand. Currently, China controls the overwhelming share of gallium production and refining, which has triggered supply risks for the global tech industries, especially considering recent export restrictions and licensing controls. This has led to price volatility and supply chain concerns. In response, critical mineral plants in the US and allied countries are being funded to process gallium and similar materials. However, this effort may take several years to scale to meaningful levels. On the technical side, gallium nitride is also facing both challenges and opportunities. Production costs are a major issue, especially compared to silicon. Much of the current gallium nitride production is done using 6-inch, that's 150 millimeter sapphire substrates. And the use of 8-inch, 200 millimeter, or even 12-inch, 300 millimeter silicon substrates has the potential to lower costs by an order of magnitude, and this would be a big advance. However, technical challenges abound due to lattice mismatch stress, thermal management, equipment compatibility, and film uniformity, just to name a few. Another area of potential cost savings is the expansion of gallium nitride foundries. There are a few gallium nitride foundries out there right now. I know Taiwan Semiconductor has an early gallium nitride foundry. Now this would allow shared development cost, standardized PDKs, and a reduction in common process expenses, just as it is done for silicon. So let's talk about devices. There are several new opportunities that are coming into focus for gallium nitride devices. Work is being done on vertical gallium nitride devices for high voltage and high power applications. A 1200 volt vertical gallium nitride device is currently available, and in theory, vertical devices could reach as high as 10 kilovolts in the future. However, at present, their major drawback is very high cost. Another emerging market opportunity is the ultraviolet LED, and this device emits ultraviolet light and has a number of uses, including rapid curing of inks and adhesives, disinfectants of air and water surfaces, medical treatment, forensics, identifying blood splatter, plant growth, and food preparation. Conclusions. As manufacturing matures and costs decline, gallium nitride is poised to become a cornerstone for the next generation of integrated circuits. Gallium nitride represents a fundamental shift in semiconductor technology, enabling higher power density and higher frequency operation than silicon. However, silicon still has the edge in certain applications like microprocessors and memories. I believe the future of the semiconductor industry will be dominated by a partnership between these two materials. Thank you for the opportunity to talk today, and it's been my pleasure.